All right. Thank you so much, everybody, to come here to spend this next hour with us. My name is Thiago Marinello. I'm a solutions architect here in AWS. And today, it's a pleasure to have Marco Pinheiro here with me. Marcos is a senior software expert at Mercado Libre. And Mark will spend time with us telling us about how Mercado Libre implements a NoOps experience for all their developers. So, but before we start talking about the Mercado Libre journey, let's talk a little bit about platform engineering, right? And what it is, and what we get here, and what the benefits and best practices that we can implement when we decide to implement our own platform. Let's take an example, the car industry. You know, if you think in the platform, it's not a new concept. Many industries use this concept to create some kind of capabilities and to use and reuse these capabilities and to create products on top of it. And if you might know, the car manufacturers, they have building platforms for their cars, and then they create new products over it. And it helps them to increase the time to market and to delivery and to delight the customers with new products. The same idea applies here when you think about platform engineering in software and in infrastructure. And if you take a look in platform engineering, we can define it or think about it as a set of practices that to identify and to building some abstractions for our developers. And what we want to achieve with this is to have a cost-effective and to increase the efficiency to use some kind of infrastructure. There is a good definition, which is in the screen, of what is a platform or platform engineering. It's a foundation of self-service APIs, tools, services, knowledge, and support, which are arranged as a compelling internal product. This definition is very good for many reasons. First, it not just talk about what is implemented as a platform. You see tools, services, which is the abstractions, APIs, but it also talks about how you drive the adoption of the platform with knowledge and support. It's very, very important to you to considering creating support for your developers to adopt the platform. But it goes further, and we have another important thing here, which is as a compelling internal product. It's very interesting when you think in your platform as a product. The same way you develop and manage products in your company for your external customers, you should think the same way for your internal platform. You should treat the platform as a product and should treat the internal customers, your developers, as your customers. We have many examples from different customers that use in EKS to create their own platforms, and most of them who thinks about product have succeeded in their journey. Well, how would you come to here, right? In our company, we have basically two different teams. We have the development teams, and you have typically our infrastructure teams. The first is responsible to create value for your final customers, and the second to keep everything running in your infrastructure. And in a company, different companies, the applications are also different. You have many different applications that requires different kind of resources, different kind of EC2 instance size, type, different kind of memory, different kind of storage, networking, maybe GPUs, maybe not. There's a lot of things that the development team needs to have access to. And we have the infrastructure team, which leads with this kind of requirements and to keep everything running, you know. what happens is that we evolve this model, right, to do 2 different teams, and we start thinking about DevOps, which is this kind of arrangement to teams that are talking with each other to deliver best results. But in practice, what happens is the development teams start creating a lot of tickets, a lot of requests to your operation teams. And it will create it will overwhelming this team with many different requests. And it's difficult to scale your company this way. And it's complex also for other reasons. In this scenario, we need to deal with a lot of standards, maybe which is difficult to implement if you have many different teams asking for many different things. We also need to deal with different kind of tools and frameworks and libraries to support many different teams. And there is no centralized way to look to your infrastructure. And there is this conflict, right? This tension between these 2 teams, and it's basically about autonomy and standardization. The development team wants to use the latest web framework that was released yesterday, but the operations team would like to have more control and more governance of your infrastructure and of what is running in production. And you need to find a balance, right? Maybe, perhaps you are in startup and we are here. We have a high autonomy, but low standardization. It typically happens in a startup because in a startup what we want to do is just to grow faster, right? You just need to acquire new customers, and we are not thinking much about the standardization. But maybe you are in an enterprise. And maybe this enterprise is in a regulated industry, like a finance or healthcare industry. You may need to implement a lot of standards, must be compliance with a lot of different requirements and regulations. But the idea is to try to find this balance. And maybe you can work to these 2 different teams and be here in the middle of this curve, which is good, very good, but you still not having all the potential benefits, which is have the autonomy and standardization. And this is where the platform engineering leads you, to have both of the 2 different dimensions. We observed a lot of customers implementing platforms, and there is some benefits that they achieve with this. The first is velocity. They start doing things more quickly. They could reduce the time to marketing because the time for a developer to start coding and to start delivering this in production is a lot more faster than without a platform. And they also could have more governance. And when I talk about governance, I mean security, compliance, and scalability or reliability. These kind of things could be partially implemented inside the platform. So the developer does not need to think about all these details of infrastructure. And also efficiency. If you have all this centralized in one place, we can look for costs, and you can manage a multi-tenant environment and reduce your costs. But also not just costs in the cloud, but costs of your team, because we don't need to train your team to be experts in Kubernetes or to be experts in all the services in cloud. You can keep the team, the development team, focus on developing applications, and the platform teams focus on developing and evolve your platform. So with that, customers are telling us that they can achieve the economy of scale when using the platform. So the platform is an investment, and it's not a short-term investment. But as the time spent, you see that the cost to create a new application and to put it in production will be reduced a lot. And it's an investment that will pay yourself. And maybe three years ago, we start thinking about or start listen about platform engineering. Before 3 years ago, it's not a common term in the industry, but 3 years ago, it started to be a trend. And today, we see many different reports for many different companies and organizations that are showing us that this kind of implementation, the use of a platform is giving them some results. So in this case, the Puppet Perforce told that the increase, the respondents of this report states that this increased the productivity, they have better quality of software, and also reduce the lead time for deployment. So there is some challenges with that. When you decide to go with a platform, and we must point this challenge here, the first is responsibility. You need to clearly define who is the owner of the platform. Typically, we have a platform development team in your company, and they must know they are responsible for that, and they must know that they are customers, again. And the developers also should work together with this team to evolve the platform. You must work backwards with your customer if you want to define and to develop something that is useful for them. The level of abstractions is a kind of a problem because nobody knows exactly, or there is no a clear definition of where the platform should stop and where the application should start. You know, for some teams, they would like to have a cluster of Kubernetes. For other teams, they would like to have just a AWS account as a platform. There is many different kinds of abstractions or level abstractions, and it must be talked with those teams, and an agreement should be done. And sometimes there is different levels. You need to live with different levels, even in the same company. The adoption of the platform is also a very important thing. There is nothing worse than develop a biggest platform with the latest technology, a beautiful platform, and nobody wants to use it. You should enforce, not enforce, you should talk with your customers, and you should prepare support for them. You should invest in training, internal training. It could be good documentation. It could be some kind of videos in your internet, in your company website to help your developers to see value and use the platform. And troubleshooting is also important because the developers are using their own environment to develop their software, and then you come with a platform and you say, wow, here is the platform, you just need to commit your code and it will be put in production. Good. But in case they have some troubles, they have some problems and they need to debug or they need to understand what is happening, you cannot say to them, well, just go and enter in this Kubernetes cluster and see what's happening. The developer will say, no, I don't want to touch this. So it's important to invest in observability tools and tools to help the developer to troubleshooting the code. Well, some best practices when we decided to build or maybe if you decided to adopt a platform are, well, build with your customers. Again, this is very important. The platform team should be in contact with the customers inside the company, the developers, and they should work together to define what is a good platform for the company. Don't boil the ocean. Don't try to do the platform that will solve all the problems. Start small. Start thinking about one problem that you have in your company that the platforms could help, and together with some real customer, try to identify a business case that the platform could help, and start developing and start validating and growing. One size doesn't fit all workloads. Sometimes a different application will need a different configuration, a different set of resources that your platform will not fit if they are offering just one option. So the platform should give to the developers options. The platform should give to the developers different kind of abstractions. If the developer wants to develop something that is using a key value store database or a document database or a SQL database, the platform should give them options. And you need to provide escape hatches. It's important because sometimes, if you are lucky in your company with a very good platform, 18 or 19% of your developers will adopt and use the platform. But there is a part of your developers that they would not use your platform, not because they don't want, but because they need different requirements, different business requirements. Sometimes they need to have escape way to implement using a different technology because the business requires it. So provide some exits or some hatches for your developers to use different kind of resources, but asking them to justify. If you have a business requirement to do that, that's great. Again, documentation and education are key. Provide a good documentation. Maybe you could automate the documentation, maybe you should write it yourself, but provide a good documentation. Developers, they don't like much to write documentation, but they love to read good documentation, right? So it's important to have this provided for your developers. And also education, training, videos, whatever that helps the developers to use the platform. And again, treat the platform as a product. This kind of mindset, it's very important. This kind of mindset help you to take care of the platform as a product and evolve it in the better way for the interests of your company and for the interests of your developers. Now, I would like to invite Marcos to talk to us and to told us about how Mercado Libre creates their own internal developer platforms.
Thank you, Thiago. Well, guys, hi everyone. As Thiago said, my name is Marcos Pinheiro. I'm a senior software expert at Mercado Libre, and I'm very excited to be here for talking more about Mercado Libre's platform, about NoOps, and how we implement Kubernetes inside Mercado Libre. For who don't know Mercado Libre is the leading e-commerce and financial services company in Latin America. Mercado Libre has been recognized by Time Magazine, Fortune Magazine, and Quinta Brands as one of the most valuable and influential companies of the world. Inside Mercado Libre, we have different business units. And here, we have some numbers about our marketplace with more than 60 million unique buyers and more than 400 million items sold. Our fintech, called Mercado Pago, has more than 50 million active users and one credit portfolio about around $6 billion. Mercado Libre today is spread across 18 countries in Latin America. Here, more numbers, but about our IT department. From 60,000 collaborators, we have 16 in IT. Part of these people are developers, technical leaders, experts, maintaining 35,000 microservices, doing almost 23,000 deploys per day, creating more than 100,000 pull requests per day, and our traffic layer, public and internal together, process more than 900 million requests per minute. We consider these numbers very nice numbers, and what do we use to support all these people, all these applications? We use Fury. Fury is our internal development platform, our IDP, and Fury was born inside Mercado Libre almost 10 years ago. Fury have been helping developers in the entire life cycle of development, starting from the code until production. Fury today provides more than 30 Fury services in a self-service way, and the most of these services are abstractions. Fury helps us in saving money on cloud, apply security standard at the company level, reducing cognitive load, and improving tech teams' productivity in a NoOps style. Here, I have one diagram that is the zero to production journey for our developers in 3 steps. Everything starts when developers need to create an application on Fury, inputting name and technology, such as Node.js, Java, Kotlin, Python, and so on. Fury, when received this request, create behind the scenes one Git repository, prepare an entire observability stack with alarms, metrics, and assign one cluster to receive application logs, and prepare one managed pipeline for the selected language. After, developers can use our Fury CLI to perform Fury Get application that clone this Git repository locally and create initial scaffolding with one endpoint and one unit test. After then develop, they can push this code to the remote repository, and when one PR, one pull request is created, or a Fury create version command is performed, both actions trigger our pipeline that executes some steps, such as run the unit test, apply the lint, and of course, build an application image in 2 different CPU architectures, x86 and ARM. Once a version is created, developers need to publish this code. So they need to create a scope. What is a scope? A scope is the Fury terminology for workloads or pool of replicas that run their application code in a specific version. So choosing the version, inputting computer resource, and selecting the region, Fury deploys this application in a managed, secure, and optimized environment, together with sidecars infused by Fury to solve traffic authentication, logs, metrics, and so on. Here, there is not necessary from our developers cloud expertise or Kubernetes expertise, because everything is managed by Fury, by our platform. But Fury abstractions are not only face our developers, but also face their applications. And here we have an example, our KVS service. KVS is a key value store service and is a Fury abstraction database that enable developer applications to store data in a key value format. Input some information on this field, on this form, name, type, description, so on. It's possible to create one KVS database. After, developers can copy this snippet using the KVS SDK, initializing the KVS client, creating an item, and persisting this item inside their code. Behind the scenes, their applications consumes the KVS API using the KVS SDK. And until 2018, we stored this information on Apache Cassandra clusters. But after this year, we switched to DynamoDB. And this change was totally transparent for our developers because the code is still the same. The SDK, the KVS is still the same, but the backend, we switched to DynamoDB. So developers do not interact with cloud providers directly. They use Fury, using our UI and our CLI. Their applications the same, consume our APIs using our SDKs. But Fury abstractions are not only a proxy. There's no make sense but one proxy on front some cloud service. Our idea is extend this service, embedding best practices, combining more than one cloud services and delivering as one only abstraction for our developers. But I'm here to talk in specific about our computing model. Where is the Kubernetes here? Easy, guys. These are how we did before we introduced Kubernetes. So here in this diagram, we have developers interacting with Fury, requesting workloads. Fury forward this request for one computer layer based on instance. This layer requests for Amazon EC2 API, EC2 instance, and generate one Docker Compose file to bootstrap not only the application container, but also our sidecars. This approach worked for us. We had concurrently more than 100,000 EC2 instances. But we found some opportunities here, opportunities about efficiency. The first problem is because using this approach, one replica is one dedicated EC2. And replicas do not use 100% of the time, 100% of their underlying resource. So this approach generates unused resource. The second problem is about idleness. And I can bring 3 examples here. Test scopes. Test scopes is when developers need to create one isolated scope to publish their code before deploying production. This is good. But developers are not testing these scopes all the time. So we have infrastructure up 24/7. The second example is about our Fury consumers scope type. Consumers on Fury is one specialized pool of replicas that subscribe one topic key. And for every message in this topic key, the message breaks in a request against these consumers. And not all consumers process messages all the time, so we have periods with idleness. And finally, our job scope types. It's only one replica, but developers can, using Fury console, configure a cron rule to trigger a specific endpoint. And seamlessly, the job duration or the cron rule, this EC2 stay alive 24/7. We try to mitigate this problem, developing some features over Fury, for example, our right sizer that recommends for our developers decrease these flavors, the scope flavors, when the available capacity do not fit with the used resource, but wasn't sufficient. Look in this diagram or in this use case, maybe we can imagine different ways to solve this problem. For example, for our consumers, maybe using Lambda, or for our jobs, using AWS batch. But our idea was extend Fury, using only one technology and transparent for our developers, because we have 35,000 microservices, so requiring some change in all these applications doesn't make sense. We made a research. We test some products, Knative, HashiCorp Nomad, and at the end, we choose Kubernetes, we choose EKS. Here, developers still requesting workloads for Fury, but now we have 3 new actors. EKS clusters, one compute API, one API inside each cluster, and a new compute layer based on clusters. The compute layer responsibility here is abstract Fury from the clusters concept, because Fury do not know Kubernetes. The compute layer do not interact with the API server. Instead, it interacts with the compute API. This API was developed by us to solve for 2 reasons. The first one is, what happens if we introduce a new EKS version in our pool of clusters? Instead, we centralize all this logic in a central layer to talk with different Kubernetes vision that could have some break chains we can here generate a new, release a new compute API to talk with this specific Kubernetes version, maintaining the same standard in our architecture. The second reason is what happens if we change from EKS to another container orchestrator? It's possible. We can do the same. We can generate and release a new compute API to talk with this specific container orchestrator, mitigating the impact in our architecture. Using this approach was possible to use Kubernetes as an engine behind Fury. So developers use Kubernetes, but they have no idea that are using Kubernetes. Also, we have computing shards, because in the previous diagram, we had only one data plane for Fury, but now we have one data plane per cluster. And this is good, because what's possible is spread all workloads that we have in well-defined clusters based on criticality and scope type. So we have clusters to job test, job production, job critical, consumers test, and so on. This has helped us in deploy our internal chains when we need to change our compute API, for example, or some Kubernetes add-on, in start from the less critical clusters and promote these chains until the most critical clusters, reducing the risk and impact some mission critical applications. Advertise yourself, guys. Well, this has also helped us in the control plane upgrades, because instead we update in place the control plane version, we can apply some concepts about immutable infrastructure. For example, it's possible to create one new EKS cluster using the last available version from AWS, test this cluster, and register this cluster in our computing layer to receive new workloads. Doing this, it's possible when developers make a blue-green deployment, for example, move these workloads to this new Kubernetes cluster in this new version. When we start to move these workloads from the old environment based on instance to this new environment, we start only with one cluster. And now we have more than 130 EKS clusters. And we only migrate 70% about all scopes that we have. Talking about deployment, Fury provides 4 main deployment strategies: blue-green, canary, safe, and migrations. Blue-green and canary are known deployment strategies, but safe and migrations are 2 specific Fury deployment strategies. Safe, behind the scene, is the blue-green. But it's lower compared with the original blue-green because it compares metrics, traffic metrics from the old pool and the new pool, the blue and the green. And if some anomaly is detected, it suggests for our developers perform a rollback. If the developers do not take an action, in 50 minutes, it rolls back the deploy automatically. Migrations, by the other hand, usually is used by us, the Fury team, to move applications between regions, clouds, and environments. And we use it a lot, this strategy, to move workloads from the old environment based on instance to this new environment based on clusters, delivering the same guarantees about the same guarantees that one blue-green deployment offer. For example, 0 downtime. Here we have more details about what happens inside our cluster when developers execute a blue-green deployment. Between our compute layer and compute API, we have an application load balancer. This load balancer is created by AWS load balancer controller that scans our clusters, and for every ingress object with some AWS specific annotations, it creates an application load balancer and registers all pods behind our compute service in that case as targets in the elastic load balancer target group. When our compute API receives this request, it translates to the API server, requests some objects. For example, namespace, service account, HPA, PDB, and a replica set. Here, we use replica set instead deployment object because we already have deployment at the platform level. So from Kubernetes, was necessary only the self-healing feature. But how our compute layer knows if all pods requested in the replica set count are ready? Well, we developed our custom Kubernetes controller called Compute Controller that reconciles the cluster state with some external state, in that case, our compute layer. So for every cluster that we have in the same region, all compute layers synchronize pods created, changed, and terminated with our central compute layer. This helps us in apply different algorithms when developers perform a blue-green. For example, move workloads between clusters. For Fury, it's the same. So when our compute layer receives a deploy, it analyzes the best cluster to receive these workloads and can choose the same or another cluster with the same characteristics. Well, having different applications in different clusters, how applications can talk one each other. So before I continue, let me introduce a little bit more the traffic flow inside Fury. Fury, many years ago, adopted service mesh as a traffic topology. And in the past, most of the service mesh tools didn't support non-Kubernetes workloads and didn't support some Fury requirements. So this is important because when we introduced Kubernetes in our architecture, there wasn't any component that synchronized these pods with our service mesh. So to solve this problem, we adopt the AWS VPC CNI as our main CNI because it's possible, using the AWS VPC CNI, assign one routable and visible VPC IP for every pod, simplifying the network access because at the network perspective, there is no barriers. After, we develop a new custom Kubernetes controller called Mesh Controller that synchronizes every pod created and terminated with our own control plane in service mesh. This helps us not only in applications in the new environment can talk one each other, but also in different environments. Well, scaling is an important feature that we have inside Fury. And using Kubernetes was possible provides more and different scaling strategies. Most of our scaling policies are based in CPU metric. We use HPA behind the scenes, but what happens when some applications cannot depend from the reactive scaling? Well, we developed the predictive CPU metric that are one model that learn the CPU pattern for every application that we have and can, using predictions, generate a result of the future CPU usage for this application, and using this approach, it's possible to scale out replicas for these applications before this spike. we developed one custom Kubernetes adapter, metrics adapter, to attach this model in the HPA policy. Also, we have the support for the RPS metric. We have some applications that use accelerators, for example, GPU. And usually these applications consume a lot of GPU, but do not consume a lot of CPU. So don't trigger our scaling policies. For this case, we build the support for developers use RPS in our platform. We also use vertical scaling with VPA together with HPA. But instead, we change running pods. We get all recommendations from the VPA and we ingest in the Fury right sizer to recommend for our developers a new blue-green deployment and the new replica pool that have these resources changed. And finally, the zero scaling. The zero scaling we did to attack the idleness problem. So we have one set of workloads inside our cluster that can detect when one application is not receiving any request. And if the developers enable this feature, it can change the replica set count to 0. Of course, this same application set can identify activity and scale out these replicas to the minimum inside the minimum configured in the HPA policy. We have two different ways to scale using Kubernetes. Applications inside our cluster and our cluster. So to scaling the nodes in our cluster, we use Carpenter as the main cluster scaler. We use Carpenter because Carpenter has out-of-box features, for example, the AWS, the spot ratio. Using virtual domains in our nodes, it's possible to decide how many spot instances we wish inside our clusters. And align this strategy with the cluster sharding that we have, it's possible to assign 100% of spots in test clusters, 80% spot, 20% on demand in some productive clusters, and in mission critical clusters using a different percentage. Together with GPA, we use cluster proportional scaler, the CPA, to apply the over-provisioning concept. So when one replica one workload needs to scale and there is no space inside our clusters, instead it waits minutes until Carpenter provisions a new node. It replaces a preemptive pod that taking seconds instead minutes, and this preemptive pod that trigger Carpenter to create a new node. Well, developers use Kubernetes, but we have Fury as one layer between developers and Kubernetes. Fury uses an imperative way to deploy all chains inside our clusters using the Kubernetes SDKs. But before the cluster admins register these clusters in Fury, it's necessary to turn this cluster a production-ready clusters. So cluster admins use a declarative way applying the GitOps concept using FluxCG to create a new Git repository, the source of truth. And for every change in this Git repository, FluxCG reconciles the external state with the internal state, creating, deleting, and changing objects inside our clusters. So we have here the same clusters, but two different ways to deploy workloads inside. Well, let's see Fury in action. I prepared one video doing the same that I present for you guys, and creating an application, creating a scope, creating a version, and deploy this application, but now from the developer perspective. I cut some parts and I accelerate the video in some parts to compact this video in 3 minutes, right? So here we are creating one application. Put a name, description, choosing the technology, and put some metadata. Here we have the Fury main page, right? After, let's perform the Fury get command to clone this repository locally, creating an initial scaffolding. Here you can see the files created and one simple endpoint created with the Fury get command. Now, we can commit and push this code to perform the Fury create version tag, in that case, alpha 1. After, we can go to the version section, and once a version is created, it's done, we can deploy this version in production. So we can go in scope section, choose the criticality, put the scope name, choose our version, configure and set up the scale to 0, for example, and put in the computer resource. There is no secrets to add in that case, so let's create our scope. Once a scope is created in active status, we can get the generated domain name and make a curve to test if everything works. The hello endpoint is the endpoint generated in the scaffolding code. And voila, it works. Now, let's change something and make a blue-green deployment. Let's make some change, changing the hello world to hello reinvent. We can see the diff here, and we can do the same. Commit this code, push this code, and perform the Fury create version alpha 2. With this version created, we can go in the deploy section, select our version, the scope, and our strategy. Blue-green that case, and it's possible configure some attributes before perform the blue-green deployment. Push application step is when Fury are waiting these pods turn in a ready state. And swap traffic is the process to move this traffic. When swap traffic is in 100%, we can make a curl again, and now we have reload reinvent. After, we can finish our blue-green to destroy the old pool and maintaining only the new pool. So, watching this video, it's possible to see that developers, there is no YAML to manage it. There is no control plans to manage it. There is no data plan to manage it. So there is no cognitive load. So it's a NoOps experience. So it's more productivity in the day by day. And this is not only for our compute model, but for the most services that we offer in our catalog. So, concluding, Fury is the foundation that supports most of these workloads with 99.95% of uptime. And using a NoOps strategy enables us to innovate, create, and switch fast, because it was possible to move workloads based in Docker Compose to Kubernetes, transparent for our developers, do not requiring them change anything. And EKS plus a NoOps strategy help us in save 30%, more than 30% in compute cloud costs. So that's it. I hope that you enjoy our session. Thank you so much. I pass the word for Thiago again.
Oh, thank you, everybody. I hope you have learned something new today. Thanks.